Hello everybody, this is Dr. Bricker here with a video for some Homework 1 help for Physics 221. So the first problem looks like this. A glass rod is charged to plus 7 nanocoulombs by rubbing. Have electrons been added or, have electrons been removed from the rod or protons added? So I'll leave that to you to answer that question. Just keep in mind electrons are the charge carriers that are more easily removed or added. So that sort of gives you an idea about that question. So this is the first homework. If you look here, this little button, review. If you're not sure of the answer, you could hit review, and that will take you to the e-text, the correct section, and you can get some help that way. Remember, do not hit request answer. That means you give up. You're not going to get another problem. You won't get a chance to get points, so never hit request answer. Part B, how many electrons have been removed or protons added? So we've got a total of plus 7 to the minus 9th coulombs. How many electrons or protons does that make up? Let's take a look at that. Okay, so you might have different numbers than me, but the numbers are randomized here. So on my homework, it's 7 nanocoulombs, which means 7 times 10 to the minus 9th. So remember, 1, either proton or electron, I'll just put electron / proton, we don't know the answer yet, has a charge of, magnitude-wise, 1.6 to the minus 19th coulombs. That's for 1 either proton or electron. We want to know how many protons or electrons do we need to get all the way up to 7 to the minus 9th coulombs. Okay, so the coulombs cancel out here, and we're just left with the number of charge carriers. So I can do 7 EE minus 9th divided by 1.6 EE on my calculator minus 19th. So something like 4.375 times 10 to the 10th charge carriers. So like 44 billion or so. Okay, let's put that in Mastering Physics and see what it looks like. Okay, so I got 4.375 times 10. So what I have is not going to work. You can't use the X as a time. You have to use the star key. So shift 8, that means times, and then 10, and then use the caret upward to get me the exponent. So times 10 to the 10th. So remember, you can't use an X here for times. You use the on my computer shift 8, which is the star symbol, and then times 10, and then the upward caret gives me the exponent. If you ever forget that, you could hit this button here, and it'll give you the keyboard shortcuts. And then I could hit submit. And correct. Okay. Very good. Let's take a look at the next one. I haven't finished that one because I didn't complete part A. That's okay. So, similar problem, plastic rod charged to negative 15, touches a metal sphere. Afterward, the rod's charge is negative 10. What kind of particles were transferred? So I'll leave part A to you. In which direction was the charged particles transferred? Same thing, I'll leave it to you. So the plastic rod was charged to negative 15, touches metal. Metal can accept charge. Afterwards, the charge is down to negative 10 nanocoulombs. And how many charged particles were transferred? Well, the amount of charge that was transferred is the magnitude of 5 nanocoulombs, right? We went from negative 15 down to negative 10. So a magnitude of 5 nanocoulombs. How many particles does that correspond to? That's the same way that we did the first problem, right? So 5 to the negative 9th coulombs. How many charge carriers is that? So same idea as the previous, the first one that we did. Okay. Let's see what we have in the next one here. A plastic sphere charged to negative 5 is near another plastic sphere, negative 14 nanocoulombs. If the spheres repel each other, which they should, they're both negatively charged, with a force of 8.8 to the minus fourth, what is the distance between them? And we want the answer in centimeters. Okay, again, you could hit review, that'll go to the correct point in the book. Again, never hit request answer. So let's take a look at this. This is a Coulomb's force law problem. Okay, so one of the charges is 5 to the minus ninth because it's 5 nanocoulombs, and that's the magnitude of it. The other magnitude of charge is 14 nanocoulombs. Don't forget that means times 10 to the minus ninth coulombs. The repulsive force is 8.8 to the minus fourth newtons. How far apart are they? So I'm writing down everything that I know. So if you have charged particles, this is the formula for the force between them. Okay, and K is a constant. 9 times 10 to the ninth newtons meters squared per coulomb squared. So the formula says force is equal to a whole bunch of stuff. This is the equation that governs the force between charged particles. Now you can do some algebra to this and solve for whatever you want to. We actually know in this problem the force is given, K is a constant, Q1 is given, Q2 is given. What we don't know is the distance between them. So how do I know how to use this the formula? Well, they give you the force between charged particles, so in your mind you have to think, okay, what do I know about that? This is what I know about that. And then you can do the algebra, solve for whatever you need to. So let's solve for R. That's what we're looking for, the distance between the particles. That's what R is in the formula. So R squared would be K Q1 Q2 divided by the force, and then you've got to take the square root of both sides. So take the square root of the right side, take the square root of the left side. The 2 goes away there. Okay, so then you can put the numbers in, and you know everything. The answer, be careful with the units, the answer will come out in meters. You'll have to convert that then to centimeters because that's what they're asking for in the problem. Okay, let's look at the next one. Okay, so let's see here. We have, here's the picture. What is the magnitude of the electrical force on charge A in the picture? And then part B. I don't think you could see part B until you finish part A, but I can do it on here. And then what is the direction of the force on charge A? Okay, so how much is the force on charge A? Remember, the force on charge A is because it's being attracted by B, but at the same time being repulsed by C. C has a larger amount of charge magnitude-wise, right? This charge is 4 times as much as this charge, but it's twice as far away. How will those effects play out? More charge means more force, but it's also twice as far away. 4 times as much force, twice as far away. You could almost guess the answer if you knew the form of the formula. But let's take a look at this. So again, we're looking at the forces on A. So let's look at them independently. Independently, I mean, let's look at the force on A from B. Let's look at the force on A from C. Okay, so these are opposites, A and B. So A is being attracted to B. So there's a force from B on A this direction. Now pretend B's not there. Let's look and see what C is doing. Positive, positive. So there's a force from C on A this way. We have to see which one's going to be larger. Here's the force formula. We've seen this already today. So the bigger the charge, the bigger the force. So you can see this charge, C, is larger than B, but it's also twice as far away. So 4 times as great force, but twice as far away. The distance away in the formula is actually squared. These are going to cancel out. The force from C on A, you can figure it out. You've got all the numbers here. Put them in. Okay. Force from C on A would be K, Q, C, Q, A, distance between C and A, 0.02 meters squared. And you can see the direction of this one, it's to the left. The force of B on A, sorry, I don't think you saw this part. Force of C on A would be K. QC, QA, distance between them is 0.02. Force from B on A would be K, QB, QA, and then the distance between them is only 1 centimeter, so 0.01 meters squared. This and this are going to turn out to be the same magnitude, but opposite directions. So while this one's A is being attracted to B, is being repulsed by C, those forces are actually equal to each other in this specific problem, so they cancel out. So no force. And I would say, put the numbers in and make sure that you see that. Okay, good. Let's look at the next one. Okay, so we've got a negative 15 nanocoulombs charge located at the origin. What is the strength of the electric field at that position? 0 and 5 centimeters, and then a couple of other positions here. The strength of the electric field here, and then the strength of the electric field there. Okay, so remember what we've done so far. We looked at the force between charged particles. Another way of visualizing what's going on is to think of charged particles as having an electric field around them, and then from there, if you knew the electric field around a charged particle, if you put another particle in the electric field, what would the force be on that particle? That's another way of looking at it. Before we look at the forces on particles and electric fields, first let's calculate the electric field because of a point charge. Okay, so let's take a look at this one. Okay, so here's a charge at the origin. We want to know the strength of the electric field here at 0,5 centimeters. So right on the y-axis there. So this is a negative charge. Remember, for negative charges, the electric field is towards it. I don't think they ask us about that, but just so you remember, towards it everywhere. The strength is given by this formula, kq over r squared. So in this problem, we have 9 times 10 to the 9th Newton meters squared over Coulomb squared. The magnitude of the charge is 15 to the minus 9th coulombs, and then divided by the distance to the point. So that's the 5 centimeters. 0.05 meters, in other words. And don't forget to square it. Okay, as far as the units go, this will come out in newtons per coulomb, right? There's a meter squared and a meter squared. The newton stays where it is, coulomb squared and a coulomb. So we end up with newtons per coulomb. That's what electric field strength is. The units are given in newtons per coulomb. Okay, so let's actually punch this in. 9. On my calculator, it's the EE button. That means times 10 to the 9th times 0.15 EE minus 9th divided by 0.05. Don't forget to square it. And we get 540 newtons per coulomb. That's the electric field strength at that point. Part B and C, I'll just kind of set up part B for us. We want to know the electric field at -5 and -5. So the charge still at the origin. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. What's the electric field strength here? This is the distance away. So you'll have to figure out what that distance is. In the first part, they just gave a 0,5 centimeters, so it's easy to see what that is. You'll have to actually calculate this distance r. You can do it, though, because you know this distance and this distance. Think Pythagorean theorem to do that. Then it's the same formula. It's just a different distance away. And same idea with part C. Okay, let's look at the next one. Okay, so the previous problem was the electric field just due to one charge. What if you have a couple of charges like we have in this problem? So there's a 1 nanocoulomb here, another 1 nanocoulomb here. We want to know the electric field strength at this point because of those two charges. So what is the strength at the here, and then also what is the direction of the magnetic field. Specify the direction as an angle above the horizontal line. Okay, so this is the horizontal line. Which direction is it? There's a lot of symmetry in this problem actually, so let's put it on a piece of paper and see what we have. Okay, so this is what the picture looks like. I just called this one up here Q1, this one down here Q2. So let's pretend Q2 is not here for a minute and look at the electric field at this spot because of Q1. So for a positive charge, the electric field is always away, remember? Positive charge goes away everywhere. Just like a negative charge, it was towards. It's the opposite. So at this point, because of Q1, the electric field is this way. I'm going to call this one E1 actually because of Q1. Now pretend Q1's not there. We've got Q2 here. So the electric field at that point would be this way because of Q1. Same magnitude of charge, same distance away. This is the distance away. We are just left with, these being the same. E2 is the same magnitude as E1. Now E2 has a part in the x direction and a part in the y direction. So E2y, E2x. E1 also has a part in the x and a part in the y. It's the y parts that actually cancel out. So let me just regroup. Q1 is here. Here's E1 pointing away. Has an x part and a y part. The electric field, because of Q2, is this way. It has an x part and a y part. The y parts actually cancel out, right? Because it's the same amount up, same amount down. So to answer question B, it's just going to be this direction, 0 degrees above the horizontal line, completely in the x direction. So we've got to figure out how much we have in the x direction. So from the symmetry of the problem, theta is 45 degrees, right? This and this are the same amount. And this is the theta I'm talking about, this angle here. So if we wanted to figure out the total electric field, the net electric field would be E1 in the x plus E2 in the x. But E1 in the x and E2 in the x are the same thing. So if I wanted to, I could just say the total is 2 E1x, because E1 in the x and E2 in the x are the same thing. So if I could just figure out E1 in the x direction, multiply it by 2, that'll give me the total amount. So this, so far, I think is the hardest problem of the semester. We're going to use Pythagorean theorem. We're going to use a little bit of trigonometry. We're going to use the new physics that we have come up with. So first of all, let's figure out how much E1 is. So from what we did before, E1 is K, magnitude of Q1, we know all this, divided by the distance between them squared. That's what this distance is. So you'll have to do a little bit of calculating to get that. So this would be 0.05 meters squared plus 0.05 meters squared. The square root of that will give you r. Kind of what you did in the last problem. So this squared plus this squared is equal to r squared, Pythagorean theorem. So then r is the square root of 0.05 squared plus 0.05 squared. Okay, so then you can get E1. Remember, that's in this direction. We need to figure out E1 in the x. Luckily, it's 45 degrees, so we're going to use sine or cosine. If you happen to mess that one up, you would be okay, because the sine of 45 and the cosine of 45 are the same thing. Let me do a better picture here. Here's E1, E1x, E1y, here's theta. So it turns out that I'm looking at this, the sine of 45 would involve E1 and the y. I don't want that one. I'm going to use the cosine of theta. That would be the adjacent side over the hypotenuse. So you'll get E1 from here. This is how we're going to get E1 in the x direction using the trig. So then E1 from the first part, cosine of theta will give you E1x. Okay, and then finally, the total electric field is twice E1 in the x. Okay, great. So remember, electric fields are a vector quantity. We need to figure out what that means is how much is in the x, how much is in the y. And luckily, the y parts of this problem cancel out. It would be a much more difficult problem if Q1 and Q2 were not actually equal to each other. Okay, let's look at the next one. All right, a parallel plate capacitor is constructed of two horizontal 16.8 diameter circular plates. So remember, a capacitor is a couple of plates that are charged up, equal magnitude, opposite charge. A 1.6 gram plastic bead with a charge of -4 nanocoulombs is suspended between the two plates by the force of the electric field between them. Okay, good. So think back to what you read in chapter 20. If you watched the video also, we talked about parallel plate capacitors. Which plate, the upper or lower, is positively charged? And what is the charge on the positive plate? Okay, so we definitely need to get a picture of this one. Let's take a look at it. Okay, so here's the mass. This is how I like to do problems. Write down what you know. Here's the beginning of a little picture. And we're trying to figure out the charge on the positive plate. And that's the diameter of the plates. So here's a charge. Gravity's pulling it down. So this is mg. We could actually suspend this if there's an electrical force that's up. Okay, so again, the electric force here is balancing the weight mg, which is down. So for this to happen, this plate would have to be positively charged. This plate would have to be negatively charged. There's a couple ways of thinking about it. This negative charge is being repulsed by the negative plate and being attracted by the positive plate. Now the electric field lines from positive to negative look like this. So the force on a negative charge is actually the opposite direction. So the force on a negative charge is this way, opposite direction of the electric field lines. So what we have is the electric force is equal to the weight. Now the electric force, this is our first problem that we've seen with this, is the charge times the electric field. Right? That's the use of having an electric field. So I can put that in here for the electric force. So QE has to be equal to mg. We're getting somewhere. We don't quite have what Q is yet. This big Q, the big Q is not in the formula. The little q is this charge. The big Q is the charge on the plate. So remember, also for the electric field, because of a capacitor, is epsilon Q over D. So then if you put this in for the electric field, you'll be able to solve this. Whoops, actually this is not D. Epsilon naught Q over A, and A is the area of the plate. Okay, so electric field because of a parallel plate capacitor, epsilon naught Q over A, so charge per area. And remember, this epsilon naught is 8.85 to the -12th Coulomb squared over Newton meter squared. It's just another constant that we have. Okay, so we can take this for the electric field then and plug it in over here. So this is the charge being suspended is equal to E, but E I know now is epsilon naught Q over A, and then that's got to be equal to mg. You still have some work to do at this point. I'm going to put dot, dot, dot. That means do some steps of algebra. Solve for Q. So you can do that. Make sure you have the mass in kilograms. Now the mass is given actually in grams. You'll have to change that into kilograms. A in the formula is the area of a plate. We're given the diameter of the plate, and they're circular, so then you can figure out the area. So remember, the area of a plate, of a circle, is pi r squared. So be careful, make sure you have the correct units there too. So you still have some work to do with this one. The physics part is set up for you. You just have to put it all together. Okay, let's look at the next one. Okay, so we've got a 0.12 gram. Be careful, it's not kilograms, it's grams. Plastic bead is charged by the addition of 1 times 10 to the 10th excess electrons. Okay, so it's going to be negatively charged. What electric field will cause this ball to be suspended in air? And what's the direction of the electric field? Okay, good. So this is like the last problem. mg is pointing down. Fe, the electric force, is pointing up. And we want to know what electric field strength will make this happen. Let's quickly sketch this one out. Okay, so we've got Fe, which I know is equal to the charge times the electric field. This is going to be equal to the weight, which is m times g. So that's being suspended. We know QE then has to be equal to mg. You'll have to figure out how much charge you have. They give you the amount of electrons. Go back and figure out what's the total charge from that. The mass they also give you. You just have to put it into kilograms. G is 9.8. I'll just write it as newtons per kilogram there. So you know everything except for the electric field. That's what you're trying to figure out. mg divided by q. Okay, excellent. So put it all together. Nice problem there. Let's look at the next one. Okay, so ninth one of the homework. Protein molecule in an electrophoresis gel has negative charge. The exact charge depends on the pH of the solution, but 30 excess electrons is typical. What is the magnitude of the electrical force on a protein in a 1500 Newton per Coulomb electric field? Express your answer in newtons. Okay, so we know the electric field strength. We know we have 30 excess electrons. You'll have to figure out how much charge that corresponds to. Right, 30 electrons, and each electron has a charge of negative 1.6 to the minus 19th coulombs. So you can figure out the total charge in coulombs. Here's the electric field strength. The force we saw from the previous couple of problems, the electric force is Q, and you can get Q times E, and E is given here. So then you can figure out the force on this protein molecule. Okay, good. And the last one. Large electric fields in cell membranes cause ions to move through the cell walls. We talked about what ions were in the chapter. The field strength is 1 times 10 to the 7th newtons per coulomb. What is the magnitude of the force on a calcium ion of charge plus E? Okay, so remember, the force is the magnitude of the charge times the electric field strength. Here's the electric field strength given in the problem, and a charge of plus E. That doesn't mean the charge is plus 1 or something like that. That means the charge is 1.6 to the minus 19th coulombs. That's what this terminology means here. So plus E means you've got plus 1.6 to the minus 19 coulombs. Coulombs is the actual SI unit. Okay, so if you do 1 times 10 to the 7th, multiply that by 1.6 to the minus 19th, you'll get the force. Okay, this is going on in our bodies right now, all this electrical stuff. Okay, any questions, email me, and I'll talk to you soon.